Now let's see how we can implement a simple enumeration in Zig to represent colors. In this code, we define an enum called color that maps specific colors to numerical values, enhancing code readability. Each color, red, green, and blue, is assigned an integer, allowing us to refer to these colors by name rather than arbitrary numbers. This approach significantly improves the clarity of our code. Next, we implement the main function, where we declare a variable myColor of type color and assign it the value color green. This directly demonstrates how to work with the enum we defined earlier. After selecting the color, we use std debug print to output the selected color. Zig makes it easy to print enum values, which are automatically converted to their underlying integer representation when required. However, for clarity and maintaining context, these enums foster better understanding by framing these integers with meaningful names. This simple yet powerful illustration shows how enums can make our codebase more understandable and maintainable, allowing us to avoid the confusion that comes with using plain integers. Now let's see how we can implement string representations for our enum values, which adds clarity when debugging or logging. In this code, we define an enum named color with 3 members, red, green, and blue. The purpose of this enum is to represent different colors in our application more effectively than using plain integers. Next, we create a function called colorToString, which takes a color enum value as an argument and utilizes a switch statement to return the corresponding string for each color. This translation between enum values and their string equivalents is crucial as it enhances the transparency of our code. When we print the selected color, we retrieve not just the numeric value but also its name, providing valuable context. In the main function, we declare a variable myColor, setting it to color green. We then call colorToString with myColor and handle any potential errors gracefully using the catch construct. Finally, we employ std debug print to display both the numeric value of myColor and its corresponding name, reinforcing the benefits of using enums for clarity and maintainability in our code. Now let's see how we can implement a secondary color enum that builds on our primary colors, ensuring we retain the original definitions. In this example, we first define an enum called primary color with 3 fundamental colors, red, green, and blue, each assigned a unique integer value. This foundational enum allows us to represent the 3 primary colors clearly. Next, we introduce a union enum named secondary color. Rather than creating separate constants for each secondary color, we derive them from combinations of the primary colors. For instance, yellow is created by adding green and red, cyan is produced from green and blue, and magenta is a result of blending red and blue. This approach cleverly keeps the original color values intact while extending the enum's functionality, demonstrating code reuse and clarity. Finally, the main function allows us to declare a variable of type secondary color and assigns it the value of yellow. The program then prints the resulting secondary color, illustrating how we can leverage enum features in Zig to create expressive and manageable code structures that represent color combinations effectively. Now let's see how we can implement methods within an enum to encapsulate related behaviors. In the code, we define an enum called color that includes 3 primary colors, red, green, and blue. What's interesting here is that we enhance the enum's functionality by adding a method named complementary. This method determines the complementary color based on the current color instance it operates on. It uses a switch statement to return the corresponding complementary color, enabling a direct mapping from each color to its opposite color. Red yields color, cyan color, green becomes color, magenta, and color blue corresponds to color yellow. Next, we demonstrate how to utilize this method in the main function. We create a variable of type color, assigning it the value color red. To find the complementary color, we invoke the complementary method directly on this color instance. The result is then printed using std debug print, showcasing how well-structured and modular the approach is. By linking colors and their complements directly in the enum, we create a clear association that enhances the maintainability and readability of our code, illustrating the power of enums in organizing related functionality effectively. Now let's see how we can implement an enumeration to handle operation outcomes in a clean and effective manner. In this example, we define an operation enum that represents 2 possible states, success and failure. This enum provides a clear and type-safe way to convey the result of an operation. The perform operation function takes a Boolean input that indicates whether the operation was successful or not. Based on this input, the function returns the corresponding enum variant, either operation success if the operation succeeds or operation failure if it does not. This encapsulation of the operations result enhances code readability and maintainability by clearly specifying what the expected outcomes are. Next, we use a switch statement to handle the result of the operation. Depending on whether the result is operation success or operation failure, we print an appropriate message to indicate the operation's status. This approach demonstrates how enums can improve error handling by allowing us to represent and manage various states in a straightforward manner, ultimately reducing ambiguity in our code execution flow. Now let's see how we can implement a combination of enums and tagged unions to represent different geometrical shapes. In this code, we define an enum called shapeType, which indicates the various types of shapes we can work with, specifically a circle, square, and triangle. This enum provides a clear and distinct designation for each shape type. Next, we create a shape union that utilizes the enum to define different structures, each representing a specific shape. For instance, the circle structure contains a radius, while the square has a side length and the triangle includes a base and height. This design encapsulates the properties relevant to each shape, allowing us to manage these different types coherently. We then implement the calculatoria function, which takes a shape as an argument and uses a switch statement to determine the area based on the actual type of shape provided. This demonstrates the flexibility of enums when they are combined with unions. Finally, in the main function, we instantiate a shape as a circle with a given radius, calculate its area, and print the result, showcasing how this structure simplifies working with different shape types while maintaining clarity in the code. Now let's explore how we can implement a finite state machine FSM using enums in Zig. We start by defining an enum called state, which represents the different states our system can be in: idle, running, and stopped. This clearly delineates the possible conditions that our program might encounter, enhancing the clarity of our code. Next, we create the handle state function, which takes the current state as an argument and employs a switch statement to determine the appropriate behavior for that state. Depending on whether the state is idle, running, or stopped, the function will print a corresponding message to the console, providing clear feedback on the system's status. Finally, in the main function, we loop through all the states defined in the state enum, passing each one to the handle state function. This simulates transitioning through the states and demonstrates how our system reacts to each distinct condition. By organizing our states into an enum and handling them through a dedicated function, we not only make the code more structured, but also facilitate easier modifications and scaling in the future. As we conclude this lesson on advanced techniques for enums, remember that these are just a few examples of how enums can enhance your code's readability, maintainability, and overall structure. Enums can keep your codebase organized while providing clarity through named constants, associated values, and methods. They allow you to handle complexity in a manageable way, especially when combined with other data structures like unions and structs. Now that you have a strong foundation with enums, the possibilities for clean and effective code are endless. Prepare to take your Zig programming to the next level as you build solutions that use these advanced enum features seamlessly. Our next lesson will delve into concurrency and task management, where you'll discover how to make your programs more responsive and capable of multitasking.